The night sky is a beautiful lie. Every star and galaxy you can see represents less than 5% of what is actually there. The rest, the overwhelming majority of our universe, is invisible. This video will reveal the hidden architecture of the cosmos, the dark matter and dark energy that shape everything from the spin of a single galaxy to the ultimate fate of all reality. You will walk away understanding why this invisible framework is the greatest puzzle in physics and how its solution could rewrite the laws of nature. We will explore why galaxies defy gravity, what force is tearing the cosmos apart, and how an ancient echo of light holds the key. What does it mean that most of the universe is a secret? Even to itself, the universe holds its secrets in plain sight, but we must learn how to read them. Our first clue to its hidden architecture came not from a telescope's brilliant image, but from a stubborn, quiet anomaly in the motion of galaxies. Think of a spinning carousel. The horses near the center make a tight, quick circle, while those on the outer edge have to travel a much longer path in the same amount of time, so they must move much faster. This is simple physics, the same rule that governs our solar system, with inner planets like Mercury zipping around the Sun far quicker than distant Neptune. For decades, astronomers expected galaxies to obey this same elegant rule. A galaxy is a vast disk of stars, gas, and dust, all bound together by gravity and spinning like a celestial pinwheel. Logic dictated that stars near the crowded, bright center should orbit quickly, while stars out in the sparse, dark fringes should creep along slowly, held by a weaker gravitational pull from the core. But when scientists like Kent Ford meticulously measured the speeds of stars in the 1970s, they found something that shattered that expectation. Stars at the very edge of a galaxy were whirling just as fast as those near the middle. It was as if every horse on that carousel, regardless of its distance from the center, was somehow moving at the exact same breakneck speed. This made no sense. According to the visible mass of the galaxy, the stars on the outskirts should have been flung off into the void, like a spinning water wheel losing its buckets. The only possible explanation was that there was far more mass present than anyone could see. A vast, invisible halo of something had to be enveloping the entire galaxy, extending far beyond its luminous edge, providing an immense extra source of gravity to hold those speeding outer stars in place. This ghostly substance, which neither emits nor absorbs light, was named dark matter. It is the hidden scaffolding, the cosmic cocoon, within which every galaxy we see is embedded. The stunning realization was this: the beautiful spiral of stars we photograph is merely the decorative frosting on a cake we cannot see. The real structure, the overwhelming bulk of the galaxy's mass, is an invisible halo that outweighs all the stars, planets, and nebulae by a factor of 5 to 1. This was our first true glimpse into the universe's hidden architecture, a silent, pervasive presence that shapes the cosmos through gravity alone. It forces a profound question upon us. What is this mysterious substance that sculpts the universe yet remains forever in the shadows? The discovery of dark matter was not the end of the mystery, but a doorway into a much grander one. If dark matter halos hold individual galaxies together, what holds the entire universe in its shape? The answer reveals a second foundational mystery: the existence of an invisible cosmic web. Picture the universe not as a random scattering of islands, but as a single, interconnected continent. If we could see with dark matter vision, the night sky would transform into a breathtaking tapestry of light and shadow. We would see delicate filaments, like threads of luminous spider silk, stretching across unimaginable voids. We would see dense knots where those threads intersect, glowing with the collected light of thousands of galaxies. And we would see vast, empty deserts, regions of profound silence where the web has not yet gathered. This is the large-scale structure of everything, and its primary architect is dark matter. After the Big Bang, tiny, random ripples in the fabric of the newborn universe were amplified by gravity. Dark matter, responding only to this force, began to clump first. It formed an invisible scaffold, a gravitational blueprint for creation. Ordinary matter, the stuff of stars and planets, was simply a passenger. As the universe expanded and cooled, clouds of hydrogen and helium gas flowed along this pre-built framework, sliding down the gravitational slopes into the waiting filaments and knots. There, under the immense pressure of their own collective weight, they ignited into the first stars and coalesced into the first galaxies. The majestic galaxy clusters we observe, and the great walls of galaxies that span hundreds of millions of light years, are not accidents. They are direct imprints, fossil records of dark matter's hidden hand. Supercomputer simulations of this process, like the landmark Millennium Run, show the eerie beauty of this growth. They start with a nearly smooth universe, and by applying only the known laws of physics and the presence of dark matter, they watch over billions of simulated years as the cosmic web emerges spontaneously. The simulated galaxies line up along filaments exactly as they do in our real telescopes. This is overwhelming evidence that the universe we see is built upon a skeleton we cannot see. Without this invisible framework, gravity would have had no head start. Galaxies would have formed slowly in isolation, scattered like lonely ships in an endless dark sea. There would be no clusters, no superclusters, no grand design. The cosmos would be a formless, dim soup, a place without architecture or address. So when you look at a map of the universe, with its stunning clusters and vast voids, you are looking at a shadow. You are seeing the ghostly outline of dark matter's influence, the hidden threads that have guided every galaxy, including our own Milky Way, to its place in the cosmic tapestry. This raises a deeper, more pressing question. If dark matter built the cosmic web, what built dark matter itself? To find those answers, we must journey back to the very first moments of time. To understand the blueprint, we must find the original architect's drawing. That drawing exists, and we can still see it today. It is a faint, cold light that fills every cubic inch of the universe, a relic from a time when the cosmos was a seething, opaque soup of energy. This is the cosmic microwave background, the CMB. It is the oldest light in existence, a snapshot taken when the universe was just 380,000 years old. Before that moment, the universe was too hot and dense for light to travel freely. Protons and electrons were constantly scattering photons, trapping the light. But as the universe expanded and cooled, those protons and electrons finally combined to form neutral hydrogen atoms. In that instant, the fog cleared. The light that had been bouncing around for all those was suddenly set free, and it has been traveling, stretching, and cooling ever since. Today, that primordial flash has been into the microwave part of the spectrum, a uniform glow just a few degrees above absolute zero. But its uniformity is not perfect, and that imperfection is everything. When we map this ancient light with exquisite precision, using satellites like WMAP, and we see a mottled pattern. It looks like a field of static on an old television, but each tiny speck of slightly warmer or cooler temperature is a message from the dawn of time. Those speckles, those minute fluctuations in temperature, are the gravitational seeds of the future. They are regions where the density of the infant universe was ever so slightly higher or lower than average. And the pattern of these seeds tells a critical story. The size and distribution of these hot and cold spots reveal the total composition of the universe at that moment. The math is clear. The observed lumpiness, the specific way matter was already beginning to clump, is far too pronounced to be the work of ordinary atoms alone. There simply was not enough visible stuff to create the gravitational wells needed to sculpt such a distinct pattern. The blueprint required a hidden ingredient, a substance that could gravitate but not interact with light, allowing it to begin collapsing under its own weight long before normal matter could. That substance is cold dark matter. The CMB is the smoking gun, proving that dark matter was not an afterthought, not a later addition to fix a galactic rotation problem. It was there, woven into the fabric of reality from the very first moments. It provided the crucial gravitational head start. While ordinary matter was still coupled to the intense radiation pressure of the early universe, unable to clump, dark matter was already quietly gathering, laying down the invisible foundations. By the time the universe was cool and dark enough for atoms to form and stars to ignite, the dark matter scaffold was already in place, a ready-made template for galaxy formation. This ancient light is therefore a fossilized map, a baby picture of the cosmos that already contains, in its subtle temperature variations, the entire fate of the cosmic web we see today. It tells us the hidden architecture was part of the original design. But if dark matter's signature is written so clearly in this first light, what does that same light whisper about the even more mysterious force that would one day tear that architecture apart's universe was a flexible stage, where mass could bend the very path of light? This prediction, gravitational lensing, gives us our most direct method for touching the invisible. When astronomers train their telescopes on massive galaxy clusters, they sometimes see something surreal. The light from galaxies billions of light-years behind the cluster does not travel in a straight line to us. Instead, it is warped and twisted by the cluster's immense gravity, creating stretched arcs, smeared shapes, and sometimes even multiple mirrored images of the same distant galaxy. It is as if we are looking at the cosmos through a giant, rippled glass. The sheer strength of this lensing effect presents a profound puzzle. The combined gravity of all the stars and hot gas we can see in these clusters is simply not enough to bend light so dramatically. There must be an enormous amount of additional mass present, mass that emits no light of its own, providing the deep gravitational well that distorts our view. This is dark matter acting as a cosmic magnifying glass. By meticulously measuring the subtle distortions in the shapes of millions of distant galaxies, a technique called weak gravitational lensing, scientists can create a map. They can trace the outline of the invisible mass responsible for the bending. The resulting maps are breathtaking. They reveal vast, smooth halos of dark matter enveloping galaxy clusters, stretching far beyond the last visible star. These halos match, with stunning precision, the predictions of supercomputer simulations. We are not just inferring dark matter exists, we are charting its geography. We can see where it pools most densely and where it thins out, confirming it forms the foundational skeleton of the largest structures in the universe. This observational proof from lensing closes a powerful loop of evidence, linking the theoretical need for dark matter to a visible, measurable effect on the light traversing the cosmos. Yet for all we have mapped its gravitational shadow, the fundamental nature of this substance remains utterly unknown. What could it possibly be made of? To answer that, the quest must leave the realm of astronomy and descend into the world of the unimaginably small. The search for dark matter has now moved from the cosmic scale to the subatomic realm. If it is a particle, what could it possibly be? For decades, one idea has dominated the hunt, the WIMP, or weakly interacting massive particle. This candidate is elegant because it solves two profound puzzles at once. In many theoretical extensions to the standard model of particle physics, particularly frameworks like supersymmetry that seek to unify nature's fundamental forces, particles like WIMPs emerge naturally. They are theorized to be heavy, perhaps hundreds of times the mass of a proton, and slow-moving or cold. Crucially, they would ignore both the electromagnetic force, making them invisible to light, and the strong nuclear force that binds atomic nuclei. Their only interactions would be through gravity and the weak nuclear force, the same force behind certain types of radioactive decay. This weakness is their defining feature, making them fantastically difficult to detect, but it also elegantly explains why they have remained hidden for so long while still being abundant enough to form the cosmic web. The experimental quest to find a WIMP is one of the most sensitive endeavors in human history. To shield from the constant rain of cosmic rays and other background noise, detectors are placed deep underground, in former gold mines or beneath mountains. Experiments like Lux-Z-PLIN and Xenon-NT use vats of ultra-pure liquid xenon, chilled to extreme temperatures, waiting for the impossible to happen, for a single WIMP from the galactic halo to bump into a xenon nucleus and create a tiny flash of light and a wisp of electric charge. Meanwhile, particle colliders like the Large Hadron Collider take the opposite approach. They try to create dark matter. By smashing protons together at nearly the speed of light, they aim to summon new particles from the incredible energy of the collisions, hoping to see a telltale imbalance in the debris that signals something invisible, like dark matter, carrying away energy. Yet, after years of searching with ever more sensitive instruments, the silence is profound. No definitive signal has been found in the deep underground labs. No missing energy signature has been conclusively spotted at the colliders. This persistent lack of detection is beginning to cast a long shadow over the WIMP hypothesis. It does not mean dark matter is not there. The cosmic evidence for its gravitational influence is overwhelming. It means the particle itself may be even more elusive or stranger than we imagined. The hunt is forcing a creative revolution. Could dark matter be composed of ancient black holes formed in the universe's first second? Could it be a vast sea of ultra-light particles, so wispy they behave more like a pervasive field than discrete matter? Or could our very understanding of gravity itself be incomplete on cosmic scales? The search continues, not just for a new particle, but for a fundamental component of reality that constitutes over 85% of all matter in the universe. Every null result, every quiet detector, is not a failure, but a signpost, narrowing the path through an invisible labyrinth and pointing us toward a truth that must be more astonishing than we have yet dared to suppose. The silence from the underground detectors is not a wall, but a door. It has forced physicists to look beyond the heavy, slow-moving WIMP and consider possibilities that sound like pure science fiction. One of the most compelling ideas emerges not from cosmology, but from the bizarre rules that govern the atomic nucleus. To understand why certain subatomic interactions are perfectly balanced, a symmetry that should not exist, a physicist named Roberto and his colleague Helen proposed an elegant solution in the 1970s. Their theory introduced a new, fundamental field to the universe. The particle associated with this field, later named the Axion by Planck, would be unimaginably different from a WIMP. It would be billions of times lighter, potentially a trillionth the mass of an electron. If axions exist in vast numbers and have the right properties, they could collectively make up the dark matter that binds the cosmos. This transforms our mental image entirely. We are no longer searching for rare, heavy bullets passing through the Earth. We are now hunting for an ocean. Picture dark matter not as scattered, invisible boulders, but as a cosmic fluid, a pervasive, wave-like field that fills every corner of space. Billions of these ultra-light particles could be passing through your body every second, their collective mass providing the gravitational glue for galaxies. Yet each individual axion is so ghostly, it barely notices the existence of atoms at all. This extreme weakness makes finding them a challenge of almost absurd precision. The most famous experiment, the Axion dark matter E or a DMX, uses a strategy that feels like alchemy. Inside a supercooled cavity, a powerful magnetic field is applied. The theory suggests that in the presence of such a field, an axion might very rarely convert into a faint microwave photon. The experiment is essentially a giant, ultra-sensitive radio receiver, slowly tuning across a vast range of frequencies, listening for a single, specific note in the cosmic static that would signal the presence of this elusive particle. The shift from WIMPs to axions represents a breathtaking expansion of the imagination in physics. It shows that dark matter could be something far stranger than just heavy, silent matter. It could be a fundamental feature of the quantum world, woven into the fabric of forces, now manifesting on the largest scales as the hidden architecture of everything. But what if we are looking in the wrong place entirely? What if the answer is not a new particle, but a revision of the oldest force we know? Perhaps the universe's greatest secret is not a hidden substance, but a flaw in our most trusted law. This is the radical proposition of modified Newtonian dynamics, or MOND. In the early 1980s, physicists confronted the same galactic rotation problem that pointed others toward dark matter, but he asked a different, more fundamental question. What if Newton's laws of gravity, which work perfectly in our solar system and on Earth, simply break down in the profound stillness of deep space? His idea was elegantly simple. He proposed that gravity does not fade with distance in the familiar, squared way when accelerations become incredibly tiny, as they are for stars orbiting in the sparse outer reaches of a galaxy. At these extremely low accelerations, gravity gets a subtle second wind, a persistent extra tug. This modified force would be just enough to hold those fast-moving outer stars in their orbits, all without needing a single particle of invisible matter. The beauty of MOND is its predictive power. For many individual spiral galaxies, the theory's equations produce near-perfect fits to their observed rotation curves, using only the visible starlight as input. It suggests the hidden architecture might not be an external scaffold, but a deeper feature of the stage itself, a gentle revision to the script of gravity written into the cosmos. Yet, every elegant theory must survive a collision with brutal evidence. In 2006, observations of a cosmic wreck known as the Bullet Cluster delivered a monumental challenge. Here, two galaxy clusters have smashed through each other at immense speeds. The collision behaved like a cosmic sieve. The clouds of hot, visible gas, slowed by friction, lagged behind in the collision's center. But the vast majority of the mass, mapped via gravitational lensing, kept right on going, separating cleanly from the visible matter. This is a direct visual signature of something that interacts only through gravity, passing through itself and the gas like ghosts. MOND, in its basic form, struggles with this, as the source of gravity is clearly not where the visible matter is. Proponents have developed more complex relativistic extensions to address such cases, but the simplicity that made MOND so appealing begins to fray. This creates a stark philosophical divide at the heart of modern cosmology. On one side, the majority view holds that we must discover new particles, filling the universe with unseen stuff. On the other, a dedicated group argues we must instead refine our oldest physical law, believing the hidden architecture is not made of matter, but of mathematics. Both paths acknowledge the same cosmic evidence, the same rotation curves, the same lensing maps. Yet they point toward utterly different realities. One seeks to complete the inventory of the cosmos. The other seeks to rewrite its operating manual. To find which path leads to truth, we must zoom out from individual galaxies and clusters and confront the behavior of the entire universe over the deepest stretches of time. The universe has a heartbeat, and in the late 1990s, astronomers listened to its rhythm across billions of years. What they heard was not a slow, fading pulse, but a startling, accelerating drumbeat. Two independent teams were studying distant stellar explosions called Type 1a supernovae, using them as cosmic mile markers to measure how quickly the universe was expanding over deep time. Everyone expected to find that the expansion was slowing down, pulled back by the collective gravity of all the matter in the cosmos, like a ball tossed upward gradually losing speed. The data revealed the opposite. The most distant supernovae, whose light had been traveling for billions of years, were fainter than they should have been. This meant they were farther away than expected. The expansion of space itself was not decelerating, it was speeding up. Some mysterious repulsive force was acting against gravity, pushing galaxies apart with ever-increasing vigor. This discovery was so shocking, so counter to all expectation, that the teams double and triple checked their work, convinced they had made an error. They had not. The universe was accelerating, and the force driving it was given a name that echoed its predecessor, dark energy. If dark matter is the hidden sculptor, dark energy is the hidden engine. It constitutes roughly 68% of the total energy budget of the cosmos, making it the dominant component of reality. Its simplest explanation is something himself once proposed and then discarded: the cosmological constant, a property intrinsic to the fabric of empty space itself. Think of a true vacuum, the emptiest possible region between galaxies. According to quantum physics, this vacuum is not nothing. It is a seething, bubbling foam of virtual particles flickering in and out of existence. This quantum activity endows empty space with a fundamental energy density, a constant pressure that, on the scale of the entire cosmos, acts as a kind of anti-gravity. As the universe expands and more space is created, more of this repulsive energy appears, leading to a runaway effect that accelerates the expansion. This forms the dual pillars of the hidden architecture. Dark matter, with its relentless gravitational pull, works to gather matter into galaxies and clusters, building the cosmic web. Dark energy, with its relentless push, works to stretch that web apart, driving galaxies away from each other over the largest scales. For billions of years, the dense, early universe was dominated by gravity's pull, allowing structure to form. But as the cosmos expanded and thinned out, the constant push of dark energy began to overtake the weakening grip of gravity. We now live in the era where this repulsive force has taken the helm, dictating the long-term fate of everything. The nature of this energy that permeates the vacuum remains perhaps the deepest mystery in physics. Is it truly a constant, unchanging property of space, as imagined? Or is it a dynamic field that evolves over time, a concept sometimes called quintessence? The answer will determine the ultimate destiny of the cosmos, whether it expands forever into a cold, dark, and isolated future, or if some other, even stranger fate awaits. This accelerating heartbeat forces us to confront a humbling truth, that the universe is governed not by the familiar matter of stars and planets, but by two invisible, opposing forces locked in a cosmic tug-of-war that began at the dawn of time. Greatest blunder has become our greatest puzzle. When he first inserted the cosmological constant, represented by the Greek letter lambda, into his equations, it was a fudge factor, a mathematical device to keep the universe from collapsing under its own gravity. He wanted a static, eternal cosmos. The discovery that the universe was actually expanding made him discard the idea, reportedly calling it his biggest mistake. The irony is profound, for today, that same discarded constant appears to be the simplest, most elegant explanation for dark energy. It is as if the universe remembered a solution its own discoverer had forgotten. Yet this resurrection has unleashed a theoretical nightmare of unimaginable scale. When physicists use the rules of quantum mechanics to calculate the energy that should be boiling in the vacuum of empty space, they arrive at a number. This number, derived from the frenetic dance of virtual particles, represents the vacuum's intrinsic energy density. Then, they look at the actual, observed value of dark energy, measured from the accelerating expansion of the universe. The two numbers should be related, they should be describing the same underlying reality, but they are not even close. The theoretical prediction is over 120 orders of magnitude larger than what we observe. To grasp the sheer size of this error, consider that the entire observable universe contains roughly 10 to the 80th power atoms. 120 orders of magnitude is a number with 120 zeros after it, a discrepancy so vast it is not merely wrong, it is a screaming paradox. It suggests our most successful theory of the very small, quantum mechanics, and our most successful theory of the very large, general relativity, are fundamentally incompatible when describing empty space itself. This is the cosmological constant problem, and it is arguably the most severe failure of theoretical prediction in all of science. It tells us we are missing a crucial piece of physics, likely the one that will finally weave gravity and the quantum world into a single, coherent tapestry, a theory of quantum gravity. Within this staggering error lies another, more haunting mystery: fine-tuning. The observed value of dark energy is not just small, it is peculiarly, precisely small. If it were significantly larger, even by a tiny fraction, The repulsive force would have overwhelmed gravity so quickly in the early universe that no galaxies, stars, or planets could ever have clumped together. The cosmos would be a featureless, accelerating void. If it were zero or negative, gravity would have eventually reversed the expansion, leading to a catastrophic Big Crunch. For a universe to produce structures complex enough to harbor life, dark energy had to be almost exactly the value we measure. This exquisite balance feels like a cosmic coincidence of impossible luck. It forces a profound question: why does the architecture of the vacuum seem tailor-made for our existence? Some physicists see this as a clue to a deeper, yet unknown, natural principle that determines these constants. Others entertain a more radical idea: the multiverse. In this view, our universe is one bubble in a vast, perhaps infinite cosmic foam, each with different physical constants and laws. We find ourselves in one where the numbers allow for galaxies and life, not because of design, but because we could not exist anywhere else. This fine-tuning is inextricably linked to dark matter. In the early universe, dark matter's gravitational pull worked against dark energy's push. The timing of their cosmic tug-of-war was everything. Had dark matter been less abundant, structures would have formed too slowly. Had dark energy been stronger, it would have shut down galaxy formation before it even began. Their invisible partnership, their precise strengths relative to each other, wrote the story of a universe that could eventually ask questions about itself. We are the product of that hidden dialogue. This hidden tug-of-war between pull and push has written a precise schedule for cosmic history. The universe did not develop at random. It followed a script authored by the invisible forces of dark matter and dark energy. For the first 9.5 billion years of its existence, gravity was the undisputed ruler. During this immense stretch of time, dark matter's relentless pull gathered the primordial gas into its invisible filaments and halos. Within those gravitational wells, the first stars ignited, their brilliant light piercing the cosmic dark for the very first time. Galaxies formed, collided, and merged, weaving themselves into the grand tapestry of the cosmic web. This was the era, the age of light, a time when the universe was busy building itself from the blueprint of dark matter. But the script contained a twist. As the cosmos expanded, the density of both ordinary and dark matter steadily diluted, weakening gravity's collective grasp across the vast voids. Dark energy, however, behaved differently. If it is a property of space itself, then its repulsive effect does not dilute, it remains constant or even grows stronger as more space comes into existence. This set the stage for a fundamental power shift. Roughly 5 billion years ago, around the time our own solar system was forming, the balance tipped. The expansive push of dark energy finally overcame the weakening pull of gravity on the largest scales. The universe crossed a threshold and entered its current phase of accelerated expansion, a chapter we are living in right now. This transition marks a pivotal and sobering turning point in the cosmic story. The great age of cosmic construction, the era where giant structures like galaxy clusters and superclusters could form, is essentially over. The hidden architecture has completed its primary work. From this moment forward, the fate of the cosmic web is one of gradual isolation and fading connection. Galaxies within bound clusters, like our own local group, will continue to dance and eventually merge under their local gravity. But the spaces between these isolated island universes will stretch at an ever-increasing rate. Over trillions of years, galaxies not already gravitationally bound to us will be swept away by the expansion of space, their light stretched beyond detection, their existence forgotten. The universe, once a vibrant web of connected structures, will become a collection of lonely galactic islands adrift in an ever colder, ever darker sea. This timeline, dictated by the hidden architecture, forces us to confront a profound truth about our place in cosmic history. We did not emerge in the universe's first fiery moments. We did not arise in its distant, cold, and isolated future. We exist in a narrow, precious window during the tail end of the age of structure, at a time when the lights are still on across the cosmos, and we can still see the grand design. We are living in the cosmic sweet spot, a temporary era of observation made possible by the precise strengths and timing of forces we cannot see. What does this privileged, yet fleeting, position tell us about the ultimate fate written by these invisible hands? The ultimate fate of the cosmos depends on a single unknown number. Guided by the properties of dark energy, cosmologists have charted several possible endings for all of reality, each more staggering than the last. The most likely scenario, based on our current best measurements, is called the Big Freeze, or heat death. In this future, the accelerated expansion we see today simply continues forever. One by one, galaxies beyond our gravitationally bound local group will be swept away by the stretching of space. Their light will be stretched, or into longer and longer wavelengths, until it fades into undetectable radio whispers and then into nothing. Within each surviving island of stars, the fuel for new suns will eventually run out. The last stars will flicker and die, leaving behind cold stellar remnants, black holes, and drifting planets. Over timescales so vast they make the current age of the universe seem like a single heartbeat, even these remnants will decay. The universe will become a profoundly cold, dark, and dilute sea of isolated particles, a state of maximum entropy where no energy can flow, no structure can form, and no change can occur. It is the ultimate silence. Yet there exists a more violent, more dramatic finale known as the Big Rip. This scenario unfolds if dark energy is not a constant, but a force that grows stronger over time. In this model, the repulsive push would intensify relentlessly. First, it would tear apart the cosmic web, separating galaxy clusters. Then, as the force grows within those clusters, it would overcome the gravity binding individual galaxies together, shredding them. The horror would come closer. Within a galaxy, the force would eventually exceed the gravity-holding stars to the galactic center. Then it would overcome the gravity-binding solar systems. In a final, cataclysmic moment, just before a finite time in the future, the repulsive force would exceed the very forces that hold atoms together. Electrons would be torn from nuclei, and nuclei themselves would be pulled apart. Reality would dissolve into a mist of fundamental particles, unable to ever interact again. The deciding factor between a slow freeze and a sudden rip is a parameter cosmologists call the equation of state of dark energy. Represented by the letter W, it is a simple number that describes the pressure dark energy exerts. If W equals exactly -1, dark energy is a constant, leading to the Big Freeze. If W is less than -1, dark energy grows, and the Big Rip becomes inevitable. Our current measurements hover right around -1, with a margin of error that still allows for either fate. These are not science fiction fantasies, but stark predictions flowing directly from the mathematics of the hidden architecture. The fate of every galaxy, every star, every atom hinges on the precise nature of this invisible energy that fills the void. It is a humbling thought that the final chapter of all existence is being written by a mystery we have only just begun to name. But this raises a profound and more immediate question. If the hidden architecture dictates our end, did it also carefully arrange our beginning? The precise strengths of these invisible forces are not just a curiosity, they are a prerequisite for our existence. This is the profound and unsettling mystery known as the Anthropic Principle. The amounts of dark matter and dark energy appear to be fine-tuned with an almost impossible precision. If the density of dark matter had been just a little bit higher, its immense gravitational pull would have caused the universe to collapse back on itself in a fiery big crunch long before the first stars could ever ignite. There would have been no time for galaxies, for planets, for the complex chemistry of life. Conversely, if dark energy's repulsive push had been even slightly stronger in the early universe, it would have acted like a cosmic hurricane, preventing gravity from ever gathering gas into galaxies. The cosmos would be a thin, featureless haze, a silent expanse with no structures at all. We find ourselves in a universe where these two titanic, invisible forces are balanced, in such a way that they allowed for a golden age of cosmic construction. A several billion-year window where galaxies could form and stars could burn long enough for life to arise on at least one small, rocky world. This is the cosmic coincidence that we exist in the brief epoch where both dark matter and dark energy are dynamically important, one having built the stage and the other now beginning to draw the final curtain. To some scientists, this exquisite fine-tuning suggests a startling possibility. Perhaps the fundamental constants of our universe, the strengths of its forces and the amounts of its hidden components, are not the only possible values. The Anthropic Principle offers a framework, stating that the universe's parameters are what they are because they allow for observers to exist within it. We do not observe a universe hostile to life, because in such a universe, there would be no one to do the observing. This line of thinking leads naturally to one of the most expansive ideas in modern cosmology, the multiverse. In this view, our entire cosmos, with its specific recipe of dark matter and dark energy, is just one bubble in a vast, perhaps infinite, cosmic foam. Other bubbles, other universes, may have entirely different laws and constants. In most, dark energy might be so strong that reality inflates instantly into nothingness, or dark matter so weak that no structures ever form. We find ourselves in one of the rare, habitable bubbles, not because of a grand designer, but simply because we could not arise anywhere else. This idea is controversial, as it can feel more like metaphysics than testable physics, yet it reframes our entire search for the hidden architecture. It asks whether the ultimate explanation for dark matter and dark energy might not be found within our universe alone, but in the statistical landscape of a reality far larger than we can ever directly see. To move from philosophy to science, we must find ways to test the untestable, pushing our technology and our imagination to their absolute limits in the hope of glimpsing the blueprint behind the curtain. The search for answers is now entering a new and decisive phase. A powerful generation of observatories, both on the ground and in space, is poised to transform our blurry map of the hidden architecture into a sharp, three-dimensional blueprint. These are not simply bigger telescopes. They are cosmic census takers, designed to collect light on an industrial scale and answer the questions that have haunted cosmology for decades. Leading this charge is the Sea Observatory in Chile. Its mission, the legacy survey of space and time, is breathtaking in its ambition. Over 10 years, it will image the entire southern sky every few nights, creating the largest astronomical movie ever made. It will track the positions and shapes of billions of galaxies, watching for the subtle, telltale distortions caused by weak gravitational lensing. This will allow scientists to create the most detailed mass map of the universe ever seen, charting the distribution of dark matter with a precision we can only dream of today. Simultaneously, by measuring how the clustering of galaxies changes across cosmic time, the survey will trace the history of the universe's expansion, putting the behavior of dark energy under a microscope. The sheer volume of data will be staggering, measured in petabytes, demanding new frontiers in computing just to process the information. In space, two dedicated missions are taking complementary approaches. The European Space Agency's Euclid telescope is already operational, its gaze fixed on mapping the geometry of the dark universe. It will measure the shapes and of over 1 billion galaxies, constructing a three-dimensional map that spans 10 billion light-years. This map will let us see how the cosmic web evolved, revealing how dark matter's scaffolding grew and how dark energy's push began to dominate. Following closely is NASA's Nancy Grace Roman Space Telescope. With a field of view 100 times larger than the space telescopes, Roman will perform wide, deep infrared surveys. Infrared vision is key, as it pierces through cosmic dust and allows us to see the most distant, ancient galaxies whose light has been stretched into longer, redder wavelengths by the expansion of the universe. By finding these earliest structures, Roman will trace the seeds of the cosmic web back to their origins, testing our models of how dark matter guided the very first moments of galaxy formation. Together, these tools represent a fundamental shift. We are moving from simply proving the hidden architecture exists to characterizing its precise properties. They will measure the equation of state of dark energy, the W parameter, with enough accuracy to finally rule out whole families of theories. They will tell us if dark energy is truly a constant or if it evolves, deciding between a slow freeze and a sudden rip for our cosmic future. They will map the lumpiness of dark matter on scales both large and small, searching for discrepancies that could hint at dark matter particles interacting with each other or revealing flaws in our gravitational laws. This is the golden age of cosmic cartography, where we stop sketching the outline and begin filling in every detail of the invisible continent that holds our visible world. The universe holds a ruler, a standard measure of distance frozen into the fabric of space itself. This ruler is called Baryon acoustic oscillations, and it is a direct echo from the cosmos's fiery infancy. In that first hot, dense sea of particles, ordinary matter and light were locked in a constant push and pull. Dense regions of matter, under their own gravity, would try to collapse, but the intense radiation pressure of the photons would push back, creating a powerful outward wave. This cycle created a series of pressure ripples, essentially sound waves, that propagated through the primordial plasma like a stone dropped into a pond. For the first 400,000 years, these acoustic waves traveled outward from every region, a booming symphony in the early universe. Then, everything changed. When the universe cooled enough for atoms to form, the fog cleared, and the photons were set free as the cosmic microwave background. In that instant, the sound waves stopped. They were frozen in place, their furthest reach creating a spherical shell of matter around each of those original dense seeds. This set a specific, universal scale, a preferred distance between points where matter would later clump. Fast forward billions of years, and that frozen sound wave manifests as a subtle pattern in the cosmic web. When astronomers create three-dimensional maps of millions of galaxies, they find that galaxies are slightly more likely to be separated by a specific distance, about 500 million light-years. It is as if the cosmos has a faint, repeating watermark, a regular spacing woven into the distribution of galaxies. This is the Baryon acoustic oscillation scale, and it is one of the most powerful tools we have. Because we know the original physical size of this standard ruler from the early universe, we can use it to measure geometry across cosmic time. By observing this preferred separation in galaxy maps from different epochs, we can see how much the universe has stretched. If dark energy is accelerating the expansion, the apparent size of this ruler will change in a specific, measurable way. It provides a clean, independent check on the supernova data, confirming the accelerating expansion and constraining the nature of dark energy. This fossilized sound wave is a gift from the dawn of time, a calibration mark etched into the heavens that allows us to measure the invisible force that now governs them. To complete this cosmic audit, we must also examine the most extreme gravitational environments the universe has to offer. The largest structures in the universe are also its most revealing natural laboratories. Galaxy clusters, cities of thousands of galaxies bound together by gravity, are not held together by the stars and gas we see. Their true anchor is a deep, invisible well of dark matter, so massive that it warps the very space around it. This extreme environment creates a unique opportunity for scientists to study the hidden architecture under conditions impossible to replicate on Earth. At the heart of a cluster, the gravitational pull is so fierce that it traps clouds of superheated gas. This gas, composed of ordinary matter, is squeezed and heated to temperatures of tens of millions of degrees, causing it to glow brilliantly in X-ray light. Observatories like the X-ray Observatory act as cosmic thermometers, mapping this searing, luminous fog. The distribution of this hot gas tells a story of pressure and gravity in balance, but when astronomers calculate the total mass needed to hold this scorching plasma in place, they find a staggering discrepancy. The visible galaxies and the hot gas together account for only a small fraction of the required gravity. The overwhelming majority of the mass is missing, a silent partner exerting its pull from the shadows. This is where a second, independent measurement comes in. By studying how the cluster's gravity bends the light from galaxies far behind it, through gravitational lensing, scientists can create a precise map of the total mass, both visible and dark. When they overlay the X-ray map of the hot gas with the lensing map of total mass, the truth becomes visually undeniable. The two maps do not align. The peak of the gravitational lensing mass, the true center of the cluster's gravity, is often offset from the peak of the hot gas. This is direct, observational proof that most of the matter is something else, something that does not glow in X-rays or visible light, something that interacts only through gravity. These cosmic laboratories allow us to literally weigh the invisible. By comparing the two maps, astronomers can calculate a precise ratio, finding that for every bit of normal matter in a cluster, there is roughly 5 times more dark matter. This ratio holds across the cosmos, a fundamental recipe for the universe's largest structures. Clusters also serve as testing grounds for the nature of dark matter particles themselves. When two clusters collide in a slow-motion cosmic wreck lasting hundreds of millions of years, they provide a critical experiment. The clouds of hot gas, made of normal atoms, slam into each other, creating friction and slowing down, much like two clouds of smoke colliding. But the dark matter, which does not interact with itself or the gas, is predicted to simply pass through. This is exactly what observations of famous mergers like the Bullet Cluster have shown. The bulk of the mass, mapped by lensing, has sailed ahead of the lagging, visible gas. This behavior is a key signature of dark matter, ruling out many alternative theories that sought to modify gravity. By studying clusters at different distances, and therefore different ages, we can watch the hidden architecture assemble itself over time, tracing how these immense gravitational anchors grew from small seeds into the dominant nodes of the cosmic web. To understand the very first seeds, however, we must look back to a time before any clusters or galaxies existed, to the moment the first starlight pierced the cosmic dark. For hundreds of millions of years, the cosmos was a silent, featureless expanse of darkness. This was the cosmic dark ages, a profound stillness that followed the release of the first light we call the cosmic microwave background. The universe was filled with a cool, neutral fog of hydrogen and helium gas, expanding quietly in the void. There were no stars, no galaxies, no beacons to pierce the universal night. Yet all the while, the hidden architecture was at work. Within the invisible halos of dark matter, the first seeds of structure were slowly, relentlessly gathering. Ordinary gas, flowing along the gravitational blueprint, pooled in the deepest wells of these dark matter cocoons. And then it happened. Sometime between 100 and 200 million years after the Big Bang, in the hearts of those primordial halos, the first nuclear furnaces sparked to life. The universe's first stars were born, and they were unlike anything that exists today. Formed from pristine hydrogen and helium, with no heavier elements, these first stars, known as population 3 stars, were likely monsters, hundreds of times more massive than our Sun. They burned with a ferocious, brilliant blue intensity and lived fast, dying in spectacular supernova explosions after only a few million years. Their birth marked the end of the Dark Ages and the beginning of a new, transformative epoch, the Epoch of. The intense ultraviolet radiation from these first stars and the earliest galaxies did not just illuminate the cosmos, it fundamentally changed its chemistry. This powerful light blasted through the surrounding neutral hydrogen gas, stripping electrons from their atoms in a process called ionization. Think of it as a cosmic sunrise happening in slow motion across the entire universe. One by one, bubbles of transparent, ionized gas began to form around these first sources of light. Over hundreds of millions of years, these bubbles grew and merged, their edges eating away at the neutral fog like fire melting a vast sheet of ice. Eventually, the entire intergalactic medium was, transformed back into the transparent, ionized plasma that fills the space between galaxies today. This epoch is the crucial bridge, the missing link between the smooth, simple universe of the CMB and the richly structured cosmos of galaxies we now inhabit. It was the moment the hidden architecture, having patiently assembled the scaffolding, finally turned on the lights. Today, our most powerful telescopes are like time machines, straining to see this dawn. The James Space Telescope, with its infrared eyes, is specifically designed to peer through the dust of time and catch the faint glow of those first galaxies. By studying them, we are not just looking at ancient stars, we are reverse engineering the dark matter halos that made them possible. The timing, the distribution, and the brightness of these first lights tell us about the properties of the dark matter that gathered them. Was it cold and slow-moving, allowing small, early halos to form, or were there other factors at play? Understanding is like reading the opening chapter of the universe's story of structure, written in ultraviolet light and dictated by gravity we cannot see. It forces us to wonder, if dark matter's hand is so clearly visible in this first dawn, could its signature be etched into the cosmos even earlier? In the very first moments of creation, what if the hidden architecture is built not from particles, but from ancient relics of creation? Among the most captivating possibilities is that dark matter consists of primordial black holes. These are not the stellar black holes born from collapsing stars, but hypothetical objects forged in the extreme conditions of the universe's first second. In that seething, dense infancy, random quantum fluctuations in density could have been amplified by the rapid expansion of space. In regions where matter was packed especially tight, gravity might have won instantly, causing pockets of the newborn cosmos to directly collapse into black holes. This idea is compelling because it requires no new, undiscovered particles. The dark matter would simply be made of compact, macroscopic objects, remnants of the Big Bang itself, that have been drifting through the cosmos for nearly 14 billion years. Their masses could range wildly, from something as small as an asteroid to something many times heavier than our Sun. A primordial black hole with the mass of a mountain would be no larger than a single atom, a speck of incredible density drifting silently through the galactic halo, invisible except for its gravity. To search for these phantom objects, astronomers use a clever trick called gravitational. If a primordial black hole passes directly between Earth and a distant star, its gravity will act as a tiny lens, bending the starlight and causing the star to temporarily brighten in a very specific, symmetric pattern. By monitoring millions of stars for these telltale flashes, surveys have hunted for a population of such lenses moving through our galaxy. The results have been largely quiet. These meticulous searches have ruled out the possibility that primordial black holes make up all of the dark matter across a vast range of possible masses, from that of the Moon to thousands of solar masses. Yet, a fascinating window remains open. For primordial black holes with masses similar to a large asteroid, current observations cannot yet say if they are abundant or rare. In this narrow range, these ancient gravitational knots could still be a significant component of the cosmic shadow. Another potential signature comes from collisions. If two asteroid-mass primordial black holes were to merge, they would ripple spacetime with gravitational waves. Future observatories, tuned to the right frequencies, might one day hear the faint chirp of such an event, a direct signal from the dawn of time. This theory beautifully ties the hidden architecture to the most extreme physics imaginable, linking the cosmic web we see today directly to the quantum fluctuations of the universe's birth. It reminds us that the answer may not lie in the realm of the infinitesimally small, but in macroscopic fossils, scattered across the cosmos like invisible stones from the first moment of everything. This opens the door to even more exotic possibilities, forms of dark matter that challenge our very definitions of matter and energy. The fine-tuning of our universe might not be a puzzle to solve, but a condition to accept. This brings us to one of the most profound speculations in modern physics, the idea that dark matter and dark energy find their explanation not within our universe, but outside of it within the concept of a multiverse. The theoretical framework of string theory, which attempts to unify all forces of nature, suggests a staggering possibility. The fundamental constants of our reality, like the density of dark energy or the abundance of dark matter, may not be unique or inevitable. Instead, they could be local bylaws, specific to our cosmic neighborhood. String theory mathematics describes a vast landscape of possible universes, perhaps 10 to the 500 different configurations, each a stable bubble with its own distinct physical rules. In this cosmic landscape, most bubbles would be stillborn. Their dark energy might be so strong that space inflates into emptiness instantly. Their dark matter might be too weak to gather any structure, or too strong and cause a swift collapse. Galaxies, stars, planets, and life would be impossible. We, however, find ourselves in a bubble where the numbers, by sheer accident, allow for a grand cosmic story to unfold. This is the anthropic reasoning applied on a scale. We do not observe a universe hostile to complexity because we could not exist there to make the observation. Our specific hidden architecture, with its precise balance of dark pull and dark push, becomes less a mystery of design and more a statistical necessity of our own existence. While this idea currently sits at the edge of testable science, it provides a powerful, if humbling, framework. It transforms the question from why are the constants so perfectly tuned for life, to what selected our particular universe from an infinite ensemble. Some physicists speculate that future discoveries might leave indirect fingerprints. Perhaps unexpected patterns or anomalies in the cosmic microwave background, the universe's baby picture, could one day suggest a collision with another bubble universe in the distant past. Or maybe a deeper theory of quantum gravity will reveal mechanisms for bubble nucleation that leave observable traces. For now, the multiverse hypothesis embeds our entire cosmic saga, with its invisible scaffolding and its repulsive energy, within an inconceivably larger and stranger meta-structure. It suggests that the hidden architecture we have been mapping so meticulously is not the foundation of everything, but merely the interior design of our own unique, habitable room in a cosmos of unimaginable variety. This is where our search for answers inevitably intersects with philosophy, challenging us to consider what it means to do science in a reality that may be fundamentally unobservable in its entirety. The invisible universe is not just a scientific frontier, it is a philosophical mirror. Every time we map the gravitational shadow of dark matter or measure the accelerating push of dark energy, we are not merely collecting data, we are engaging in a profound act of inference. We are observing the visible universe's behavior and concluding that the only coherent explanation, is the existence of these vast, unseen components. This logical process, called inference to the best explanation, is the bedrock of cosmology, yet it also places a fundamental boundary around our knowledge. We are like detectives who have found the perfect suspect, with motive and opportunity clearly established, but we have never seen their face or heard their voice. The gravitational evidence is overwhelming, but the direct evidence remains elusive. This invites a humbling question, one that echoes through the history of science. Are we describing reality, or are we describing the limits of our current models? Consider the orbit of the planet Mercury. For centuries, astronomers tracked a tiny, persistent wobble in its path that Newton's laws of gravity could not explain. The best inference at the time was the existence of another planet, Vulcan, orbiting even closer to the Sun. Telescopes searched for it in vain. The real explanation was not a hidden object, but a hidden truth about gravity itself. His theory of general relativity revealed that mass curves spacetime, and Mercury's orbit was simply following that curved geometry near the Sun's immense mass. The problem was not a missing planet, but an incomplete theory. Could our dark universe be a similar placeholder? The stunning success of the Lambda-CDM model, which pairs cold dark matter with a cosmological constant, is undeniable. It predicts the cosmic web, the fluctuations in the ancient light, and the accelerating expansion. But its very success rests on two enormous unknowns. This forces a philosophical pivot in our search. We must remain open to the possibility that dark matter and dark energy are not things in the traditional sense, but emergent phenomena, shadows cast by a deeper understanding of quantum fields or a modification of gravity that operates on cosmic scales. This is not a failure of science, but its greatest strength. The history of discovery is a story of boundaries being redrawn. Each mystery that resists conventional explanation becomes a signpost pointing toward a more fundamental layer of reality. The search for the hidden architecture, therefore, is as much about expanding the horizons of human comprehension as it is about finding a specific particle. It is a process that cultivates intellectual humility, reminding us that our most successful theories are maps, and a map is not the territory. This philosophical journey has remarkably practical echoes right here on Earth. The quest to detect a wisp of dark matter has driven unprecedented advances in ultra-pure materials, quantum sensors, and data analysis. The need to simulate the cosmic web has pushed supercomputing to its limits, developing algorithms that now model climate systems and biological proteins. By straining to see the invisible threads of the cosmos, we are inadvertently weaving a stronger technological fabric for our own world. The greatest gift of this mystery may not be the final answer, but the new ways of thinking and seeing it forces us to invent along the way. The quest to see the unseen has always been a powerful engine for human invention. Our attempts to detect dark matter, a substance that may ignore almost everything, have forced us to build instruments of almost impossible sensitivity. This drive has not just peered into the cosmos, it has revolutionized technology here on Earth, creating a cascade of innovations with applications far beyond astrophysics. To shield their experiments from the constant rain of cosmic particles, scientists had to become masters of silence. They built laboratories deep underground, in former mines and beneath mountains, and developed techniques to create the quietest environments on the planet. This expertise in low background science is now a precious tool. It is used to screen for incredibly faint traces of radioactive material in medical isotopes, ensuring patient safety. It safeguards nuclear facilities by detecting the most minute signatures of proliferation. The very art of listening for a whisper in a storm has made our world more secure. Meanwhile, the heart of the experiment, the detector itself, demanded a new kind of purity. To have any hope of spotting the phantom touch of a dark matter particle, every component had to be crafted from materials with near-perfect cleanliness, free from even trace amounts of natural radioactivity. This relentless pursuit has pushed material science to its limits, leading to breakthroughs in ultra-pure metals and crystals, and novel methods of contamination control that now benefit semiconductor manufacturing and pharmaceutical production. Perhaps the most widespread gift of this search lies in the realm of data. These experiments generate torrents of information, a digital ocean in which the signal of a potential dark matter interaction would be a single, unique drop. To find it, scientists had to invent new ways to sift, sort, and recognize patterns in colossal datasets. The machine learning algorithms and statistical techniques forged in this crucible are now ubiquitous. They help Wall Street model complex risks, enable weather agencies to predict severe storms with greater accuracy, and allow biologists to map intricate gene networks. The search for the universe's hidden architecture has, quite literally, taught us how to find meaning in noise on a planetary scale. Furthermore, these grand collaborations, like the Large Hadron Collider or the global network of dark matter observatories, are feats of human organization. They bring together thousands of scientists, engineers, and technicians from dozens of nations, speaking a common language of curiosity. This model of international big science not only advances knowledge, it builds bridges of cooperation and trains a generation of problem solvers whose skills in systems engineering, cryogenics, and advanced computing flow directly into the global economy. The profound irony is beautiful. In straining to touch the most elusive substance in the cosmos, we have been forced to dramatically improve our grasp on the tangible world around us. This demonstrates a timeless truth, that the journey to answer our deepest questions about the universe often provides the very tools we need to better our own lives. As we stand on this foundation of new knowledge and new capability, we are compelled to look forward, to ask how this understanding of the cosmos might one day shape a future far beyond our current imagination. The search for the universe's hidden blueprint has already reshaped our world, but its greatest impact may lie in a future we have only begun to imagine. For a civilization that reaches for the stars, dark matter will not be an abstract curiosity, but a practical reality of the interstellar environment. The invisible halos that cradle every galaxy are more than scientific puzzles. They are the gravitational geography of the Milky Way. To navigate the vast ocean between stars, future explorers would need a chart of these unseen masses. Plotting a course from one star to another would require knowing not just where the bright stars are, but where the deep, dark gravitational wells lie. A ship passing too close to a dense knot of dark matter could experience unexpected tidal forces or gravitational lensing effects that distort its view of the cosmos, potentially throwing its navigation dangerously off course. Understanding this hidden architecture would be as essential to safe interstellar travel as nautical charts were to ancient mariners avoiding hidden reefs. It transforms the galaxy from a scattering of points of light into a three-dimensional landscape of visible and invisible terrain. This knowledge could unlock more than just safe passage. It might one day inspire profound engineering. While firmly in the realm of speculation, some futurists and physicists contemplate whether a sufficiently advanced civilization could use dark matter halos as cosmic infrastructure. The immense, smooth gravitational field of a dark matter halo could, in theory, serve as a stable anchor for hypothetical megastructures, like a sphere, on a scale we can barely conceive. The halo's gravity would be a uniform, reliable foundation in the void. More speculatively still, if dark matter particles do interact with each other in ways we have not yet detected, a future science might discover how to catalyze their annihilation, tapping into the immense reservoir of mass energy locked in the galactic halo. This is not a prediction, but a reminder that mastering the fundamental components of the universe has always been the precursor to technological leaps. First, we understood steam, then electricity, then the atom. Understanding the hidden 85% of all matter would be a transformation of a different magnitude entirely. Beyond navigation or energy, the deeper revelation of dark matter would become a cornerstone of a cosmic culture. For a species living among the stars, the philosophical realization would be inescapable. The universe is made mostly of something other than us. The planets, the stars, even our own bodies, are a rare and special form of cosmic afterthought, a delicate froth on the surface of a deep, dark sea. This perspective would fundamentally alter art, philosophy, and our sense of place. Just as the Copernican revolution moved us from the center of the solar system, and the discovery of billions of galaxies moved us from the center of the cosmos, the full integration of dark matter moves us from being made of the primary substance of reality. We are not the standard stuff of the universe, we are the exquisite exception. This cosmic humility could foster a unique identity for a spacefaring civilization, one defined not by dominion over nature, but by a graceful navigation of a reality mostly unseen. The ultimate question then shifts from what dark matter is to what our relationship with it could become. The hidden architecture defines the stage upon which any future history will be written. To ignore it would be to build a house without a map of the land it sits upon. The mastery of this invisible framework would mark the transition from a species that simply lives in the cosmos to one that truly understands its home. This leads us to a final, unifying thought. If dark matter and dark energy are the dual pillars of everything, what overarching principle might finally explain why this specific, strange, and habitable architecture came to be? The very nature of dark matter presents a foundational challenge for any future beyond observation. If it is a particle like a WIMP or an axion, its defining feature is an almost perfect refusal to interact with the world we know. A mountain made of this substance could drift straight through our planet, its gravitational signature a faint whisper lost in the noise of Earth's own mass. From an engineering perspective, something that ignores light, electromagnetism, and the strong nuclear force is essentially untouchable with any technology based on those forces. Its profound darkness is what makes it the universe's hidden architect, but also what seems to place it forever beyond our physical reach, a ghost we can map but never grasp. This suggests our relationship with the hidden architecture may always be one of passive understanding, not active use. Yet the history of science cautions against such absolute limits. For centuries, electricity was a curious but useless phenomenon, a parlor trick of static sparks. The deeper understanding of electromagnetism provided by scientists like Faraday and Maxwell transformed it from a curiosity into the foundation of modern civilization. A complete theory of dark matter, one that successfully unites it with the standard model of particle physics, would represent a similar seismic shift in comprehension. It might reveal that dark matter is coupled to normal matter through some ultra-weak, undiscovered fifth force, or that its particles can be manipulated under conditions we have not yet imagined. While harnessing galactic dark matter halos remains a prospect for the far, speculative future, the journey to a full theory will inevitably uncover new layers of quantum reality, with applications we cannot currently predict. The process of solving this puzzle forces us to invent new mathematics, new detectors, and new ways of thinking about space, time, and substance. For the present, however, we remain cosmic cartographers, meticulously charting a continent we cannot land upon. This delicate position, relying entirely on inference from subtle gravitational effects, places an immense burden on our methods. It forces a critical question upon every scientist in the field. How do we ensure we are mapping a true hidden reality, and not simply being misled by the imperfections in our own lens? Every map is only as reliable as the tools used to draw it. In the grand project of cosmic cartography, our most dangerous enemy is not the darkness, but a subtle, persistent form of bias known as systematic error. These are not random mistakes, but consistent flaws in our instruments, our methods, or our assumptions that can steer an entire field in the wrong direction. The initial, stunning discovery of the universe's accelerating expansion rested on the light of distant supernovae. But a single thread of evidence is fragile. To build an unshakable case, scientists needed a chorus of independent voices. They turned to the cosmic microwave background, the ancient echo that reveals the universe's infant geometry. They measured the Baryon acoustic oscillations, the fossilized sound waves frozen in the galaxy distribution. They counted the abundance of massive galaxy clusters across time. Remarkably, these completely different methods, each probing distinct cosmic epochs with different physics, all sang the same song. They converged on a universe dominated by dark energy and dark matter. This cosmic concordance is our strongest safeguard, a multi-layered confirmation that the hidden architecture is real. Yet, even the most beautiful symphony can contain a note of discord. A persistent tension has emerged in modern cosmology, known as the tension. Measurements of the universe's current expansion rate, using late universe markers like supernovae and certain stars, consistently return a value that is faster than the rate predicted by extrapolating from the early universe data of the cosmic microwave background. The discrepancy is small but stubborn. persisting even as measurements become more precise. This could be the first thrilling crack in our model, a hint of new physics, perhaps a dark energy that evolves, or an exotic form of dark matter that influenced the early cosmos. Or it could be a warning sign. It might indicate a subtle, unaccounted-for systematic error hiding in one of our pristine measurements. Perhaps our understanding of how certain stars behave as standard candles is imperfect, or there is a tiny bias in how we interpret the ancient microwave light. The scientific process is designed for this very moment. To combat systematic error, cosmologists employ rigorous, self-critical methods. They perform blind data analysis, where the final answer is hidden even from the researchers until all procedures are locked in, preventing unconscious bias. They champion open data policies, allowing independent teams to scrutinize each other's work. Every claim is subjected to a gauntlet of cross-checks from different probes. This relentless scrutiny is not a sign of weakness, but the core strength of the scientific endeavor. It means that deciphering the hidden architecture requires more than powerful telescopes. It demands the finest and most carefully calibrated instruments of human reason. The map of the invisible must be drawn with humility and an unwavering commitment to finding our own potential mistakes. This vigilance now guides the next generation of experiments, designed specifically to resolve these tensions and either confirm our standard model or reveal the new physics waiting just beyond its edge. The quest to understand the hidden architecture requires listening to the faintest whispers from the dawn of time. A new generation of instruments is being built for this singular purpose, an experiment of staggering scale known as CMB-S4. This is not a single telescope, but an entire observatory network, a coordinated army of hundreds of thousands of ultra-sensitive detectors stationed at the two best places on Earth to see the pristine sky: the high, dry desert in Chile and the frigid, stable air above the South Pole. Their target is the cosmic microwave background, but their ambition is to see it in a way we never have before, with a resolution so sharp it could detect the fingerprints of the universe's very first moment. The CMB is more than just a baby picture of temperature. It also holds a record of polarization, a specific orientation in the direction of its ancient light waves. Within that polarization map, theorists predict the existence of an incredibly subtle pattern, a faint, swirling signature known as primordial B modes. Finding this pattern would be one of the greatest discoveries in the history of science, for it is considered the smoking gun evidence for cosmic inflation. Inflation is the theory that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion, smoothing it out and planting the quantum seeds that would later grow into galaxies and the cosmic web. If inflation happened, the violent stretching of spacetime itself would have generated ripples in the fabric of reality, primordial gravitational waves. These waves, traveling across the cosmos for over 13 billion years, would have left their unique, curling imprint on the polarization of the CMB-S4 is designed to be sensitive enough to find that imprint. The significance of this hunt is almost beyond comprehension. Detecting these primordial waves would be a direct observation of the universe, when it was only a trillionth of a trillionth of a trillionth of a second old. It would probe energies a trillion times higher than anything the Large Hadron Collider can ever achieve, taking us back to the epoch where gravity and the quantum world were unified. It would tell us how the seeds for all structure, including the dark matter scaffolding, were first generated from quantum fluctuations blown up to cosmic size. Beyond this primary goal, the experiment's exquisite maps will act as a supreme cosmic accountant. By measuring how the CMB light is subtly distorted as it travels through the growing cosmic web, CMB-S4 will weigh the neutrino, pinning down how many varieties exist and determining their tiny masses. It will also place the constraints yet on the nature of dark energy and the properties of dark matter, testing whether they have interacted with each other or with radiation across cosmic history. This experiment beautifully connects the largest scales of the cosmos to the smallest scales of quantum physics. It seeks to show us the instant the blueprint was drawn, the moment the hidden architecture received its fundamental instructions, written in gravity waves on the very first light. Gravity has a sound, and soon we will have an ear to hear it. While ground-based observatories like LIGO have captured the high-pitched chirps of stellar mass black holes merging, a new observatory will tune into the universe's deepest bass notes. The Laser Interferometer Space Antenna, known as LISA, is a mission of breathtaking ambition. It will not be a telescope on a mountaintop, but a constellation of 3 identical spacecraft, flying in a precise triangular formation millions of kilometers apart, trailing the Earth in its orbit around the Sun. At the heart of each spacecraft will be a pair of solid gold-platinum cubes, floating freely in a near-perfect vacuum, shielded from all forces except gravity. LISA's fundamental task is to measure the distance between these cubes with a laser of almost impossible precision. It is essentially a gravitational wave detector with arms 2.5 million kilometers long. When a gravitational wave, a ripple in spacetime itself, passes through this triangle, it will minutely stretch and squeeze the space between the cubes. LISA's lasers will detect this change, a shift smaller than the width of a single atom across that vast interstellar distance. This will open a low-frequency window on the cosmos, allowing us to hear what our eyes cannot see. The first sound will be a cosmic hum, a steady background drone generated by the millions of binary white dwarf stars orbiting each other in our own Milky Way galaxy. But beneath that hum, LISA will listen for the monumental crashes that shape the universe. It will detect the mergers of supermassive black holes, monsters with masses millions or even billions of times that of our Sun, residing at the centers of galaxies. As 2 galaxies merge, their central black holes will eventually spiral together in a final, violent dance, sending powerful gravitational waves ringing across the cosmos for billions of years. LISA will hear these events from the farthest reaches of space and time, and here is where it connects directly to the hidden architecture. As those gravitational waves travel for eons across the universe, they pass through the vast filaments and halos of dark matter that make up the cosmic web. Just as light is lensed by gravity, these spacetime ripples can be subtly distorted, their frequency and amplitude shifted by the invisible mass they encounter. By analyzing these distortions in the signals from many black hole mergers, scientists could reconstruct a map. They could trace the distribution of dark matter along the line of sight, using gravitational waves as a brand new probe to weigh the unseen. Furthermore, if a component of dark matter is made of primordial black holes from the universe's first second, LISA might be the instrument to find them. It could detect the mergers of these ancient asteroid mass objects, providing a direct gravitational witness to the era of creation itself. LISA represents a fundamental shift in how we perceive the cosmos. For centuries, we have relied on light, from radio waves to gamma rays. Now we are adding a new sense, gravitational hearing. This is the essence of messenger astronomy, combining sight and sound to build a complete picture of reality. The data from LISA, the Observatory, the Roman and Euclid telescopes, and CMBS-4 will create a symphony of information. The challenge and the promise of our time is learning how to listen to all these voices at once, to hear the single story they tell about the dark universe we are just beginning to understand. The hidden universe reveals itself not only through telescopes, but through the hum of a supercomputer. To interpret the coming flood of data from our new observatories, cosmologists must first build entire realities from scratch. This is the era of computational cosmology, where the quest to understand dark matter and dark energy has moved into the realm of pure mathematics and silicon. Inside the world's most powerful supercomputers, scientists run what are called n-body simulations. These are not simple animations. They are rigorous mathematical experiments that begin with a universe of almost perfect smoothness, sprinkle it with billions, even trillions, of simulated dark matter particles, and then set the clock running forward from near the Big Bang. The only rule governing these digital particles is gravity. Watch as gravity works its magic over billions of simulated years. Those particles begin to attract one another, slowly at first, then with gathering speed. They flow along invisible gradients, clustering into halos, weaving themselves into filaments, and leaving behind vast, empty voids. What emerges from the chaos is breathtaking, a perfect digital replica of the cosmic web, a ghostly skeleton of dark matter that mirrors the large-scale structure of our real universe. But a skeleton alone is not enough. The latest generation of simulations, with names like TNG and FLAMINGO, go much further. They incorporate the messy, complex physics of the ordinary matter that rides upon the dark scaffold. Algorithms model how gas cools and collapses within dark matter halos, how it fragments to form stars, how those stars live, die, and explode as supernovae seeding space with heavy elements. They even simulate the growth of supermassive black holes at galactic centers, whose energetic outbursts can heat surrounding gas and shut down star formation. The goal is to create a synthetic cosmos so complete, so rich in detail, that it can be placed side by side with the maps from the Observatory or the Euclid telescope for a direct, point-by-point comparison. This virtual universe becomes our ultimate laboratory. Here, we can perform experiments impossible in reality. We can tweak the fundamental parameters of existence. What if dark matter particles were slightly warmer, moving faster in the early universe? We run the simulation and see if galaxies form too late or too early. What if dark energy is not a constant, but a dynamic force that weakens over time? We adjust the equation and watch how the cosmic web expands and evolves across 13.8 billion simulated years. We can test exotic theories, like self-interacting dark matter that scatters off itself, or primordial black holes that seed early galaxy formation. In each case, we ask one simple, profound question: does this simulation, built with these specific rules, produce a universe that looks like the one we actually live in? The synthetic galaxies must have the right shapes, sizes, and colors. They must cluster together in the observed patterns. Their internal chemistry must match what we see in real stars. It is a process of cosmic matchmaking, where we refine our theories by seeing which ones can successfully grow a familiar cosmos from first principles. Through this digital mirror, the hidden architecture is not just mapped, it is reverse engineered. The overarching pattern emerging from this synthesis is one of remarkable success, but also of persistent, telling tensions. Our standard model of cold, dark matter and a cosmological constant builds a virtual universe that is stunningly similar to our own on large scales. Yet, when we zoom into the fine details, certain discrepancies appear. Simulated galaxies sometimes have too many stars at their cores, or their dark matter halos are denser in the center than some observations suggest. These tiny mismatches between the digital and the real are not failures. They are the most valuable clues we have. They are the places where our model might be cracking, where the true, deeper nature of dark matter or the influence of dark energy might be leaving a subtle fingerprint. The synthetic cosmos thus becomes a discovery engine, highlighting exactly which questions our next generation of telescopes must answer. It transforms cosmology from a science of observation into a science of simulation and validation, where we learn about reality by building countless alternatives and seeing which one truly feels like home. The most profound lesson from our digital cosmos is not its scale, but its simplicity. Every simulation that successfully grows a universe like our own begins with almost nothing, a nearly smooth expanse of space seeded by the faintest of quantum ripples. The rules programmed into these virtual worlds are equally sparse. Gravity attracts, gas cools and collapses, stars form and explode. There is no top-down design for a spiral galaxy, no blueprint for a supercluster. Yet, from this sparse starting point and these handful of laws, the entire breathtaking complexity of the cosmic web emerges spontaneously, like a snowflake crystallizing from water vapor. This is the foundational pattern of emergence, where simple, low-level interactions give rise to intricate, high-level order that could never be predicted by studying the components alone. The hidden architecture of dark matter is the essential silent partner in this cosmic dance. By forming stable, long-lasting gravitational wells, it creates the calm harbors within the expanding universe. Into these deep, invisible basins, the ordinary matter can flow. And here, the messy, dissipative physics of baryons takes over. Gas clouds collide, radiate away heat, and fragment. Gravity pulls the densest knots together until nuclear fusion ignites, birthing stars. Those stars live, die, and explode in supernovae, enriching the cosmos with heavy elements and stirring the galactic pot with shockwaves. What we see as the magnificent, structured beauty of a spiral galaxy, with its luminous arms and brilliant core, is not a pre-written script. It is an emergent story, a narrative written in real time by the constant conversation between the invisible, stable scaffold of dark matter and the dynamic, creative chaos of visible matter. Your own existence is a product of this emergence. The carbon in your cells, the iron in your blood, were forged in the hearts of stars that could only form because dark matter halos provided a gravitational cradle deep enough and stable enough for them to be born. We are not just living in a universe with dark matter, we are living because of it. Our complex reality is a higher-level pattern woven from the interplay of dark and light. This raises a tantalizing possibility. If both the hidden and visible components of the cosmos arise from the same simple beginnings, could they share a deeper, more unified origin? The grandest quest in science is not for a new particle or a new map, but for a new language. For over a century, physics has spoken in two distinct, wildly successful dialects. The first is quantum mechanics, the language of the impossibly small, describing particles and forces with probabilistic certainty. The second is general relativity, the language of the immense, describing gravity as the curvature of spacetime itself. The problem is, these two languages are mutually unintelligible. They cannot hold a conversation about the same event, such as the center of a black hole or the first instant of the Big Bang. To truly understand the hidden architecture, we must find a single, unified tongue. This is the search for a theory of quantum gravity, a framework where gravity is not a curve in the stage, but a player on it, governed by the same quantum rules as everything else. This is not just an academic exercise. It is the necessary step to answer our deepest questions. What is dark matter at its core? Is dark energy a constant or something that evolves? What triggered cosmic inflation? A successful theory of quantum gravity would not treat these as separate puzzles, but as different chapters of the same story written from a single set of first principles. The leading candidates sound like poetry from a distant future. String theory proposes that the fundamental ingredients of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrational modes of these strings could give rise to every particle and force we see, including the carrier of gravity, the graviton. In this view, dark matter might be a specific, stable vibrational pattern of a string we have not yet detected. Dark energy could be tied to the way extra, hidden dimensions of space are curled up at every point. Another approach, loop quantum gravity, takes a different path. It suggests that spacetime itself is not smooth and continuous, but woven from a fabric of tiny, discrete loops, a quantum foam. Here, the universe has a smallest possible unit of space and time. In such a framework, the smooth acceleration of dark energy or the distribution of dark matter could emerge from the statistical behavior of this granular spacetime, much like the pressure of a gas emerges from the collective motion of countless molecules. These ideas are breathtaking in their scope, but they share a profound challenge. They operate at energy scales so far beyond our particle colliders, and at distances so much smaller than anything we can probe that direct experimental confirmation seems, for now, out of reach. This has led to even more radical speculations. Some theorists propose that dark matter and dark energy are not separate entities at all, but two different faces of a single, underlying field, a unified dark sector that manifests as attraction on galactic scales and repulsion on cosmic ones. Others explore the holographic principle, the mind-bending idea that our entire three-dimensional universe, with all its galaxies and dark matter halos, is a projection of information encoded on a two-dimensional surface at its boundary. In this view, dark energy and dark matter would not be things within the universe, but emergent properties of how that cosmic information is processed and displayed. While these concepts are highly speculative, they are the engines of theoretical progress. They force physicists to think in entirely new geometries, to question the very nature of space, time, and substance. A successful theory would achieve something far greater than just fitting the data. It would reveal the hidden architecture not as a collection of mysterious ingredients we must add to our equations, but as an inevitable, beautiful consequence of a deeper, more elegant logic. The cosmic web, the accelerating expansion, even our own existence, would be seen as necessary features of a coherent whole. This is the ultimate goal, to move from a map of the unseen to the fundamental code that generated it. This grandest of quests, however, does not happen in isolation. It is fueled not just by equations on a blackboard, but by a collective human curiosity that reaches far beyond the walls of any laboratory. This grand narrative of dark matter and dark energy has become a cornerstone of our shared cultural imagination. The story of the hidden architecture is no longer confined to academic journals. It is told under the domes of planetariums, woven into documentary films, and explored in best-selling books that translate complex data into stories of cosmic mystery. This public engagement is not a secondary effect of the science. It is a vital pillar that supports the entire endeavor. When a stunning visual simulation of the cosmic web fills a giant screen, or a clear analogy explains how dark matter bends light, it does more than inform. It ignites a sense of wonder that can define a young person's future, potentially inspiring the next visionary theorist. This widespread curiosity directly fuels the mission, as public support helps secure the substantial funding required for telescopes that peer back to the dawn of time and detectors buried deep underground. Beyond practical support, this story enriches our culture with a profound cosmic perspective. To truly grasp that the stars and planets we see are a mere 5% of reality is a deeply humbling experience. It recontextualizes our place in the cosmos, not as the center of everything, but as curious inhabitants of a thin, luminous crust on an ocean of unseen forces. Yet this humility is paired with an immense source of inspiration, the relentless, collaborative human effort to map the unknown. From international teams operating space telescopes to citizen scientists classifying galaxies online, the quest fosters a powerful sense of shared global endeavor. Every time someone looks up at the night sky and wonders about the invisible scaffolding holding it all together, they are participating in this centuries-old human project, connecting to a fundamental drive to understand our home. This widespread fascination, however, sometimes leads to common misconceptions that can cloud the beautiful clarity of the science. One frequent idea is that dark matter and dark energy are simply placeholders for our ignorance, names we give to a gap in our knowledge that will eventually be explained away. The reality is far more compelling. These are not vague ideas, but precise, measurable components with defined gravitational effects. The evidence is not a single observation, but a converging chorus from galactic rotation, gravitational lensing, the cosmic microwave background, and the large-scale structure of the universe. They are the best explanation for a vast suite of independent data. Another common thought is that scientists are searching for dark matter in a single way, perhaps only in deep underground labs. In truth, the hunt is a multifaceted campaign using particle colliders, astronomical surveys, and precision studies of the early universe, a testament to the creative breadth of the investigation. Perhaps the most poignant misconception is that this hidden universe is irrelevant to our daily lives. While its particles may pass through us unnoticed, the quest to find them drives technological innovation in computing, materials science, and data analysis, tools that shape our modern world. More deeply, the cosmic perspective it fosters, of a universe vast, strange, and mostly unseen, can subtly reshape how we see our own planet and our place within it, reminding us that we are part of a grand, ongoing story of discovery. Clarifying what dark matter is not can be just as important as defining what it might be. Let's dispel a few persistent myths that often cloud this profound mystery. First, dark matter is not antimatter. Antimatter is a known, well-studied form of matter where particles have opposite electrical charges to their ordinary counterparts. When matter and antimatter meet, they annihilate in a flash of energy. We create antimatter in laboratories, and we see its signatures in cosmic ray interactions, but it simply does not exist in the vast quantities needed to explain the gravitational pull of galaxies. If dark matter were antimatter, we would see constant, brilliant flashes of gamma rays from annihilation events all across the cosmos, a fireworks show that simply is not there. Second, dark matter is not simply ordinary matter hiding in the dark. For a time, astronomers considered the possibility that the missing mass was made of massive compact halo objects, or machos. This category includes faint, failed stars known as brown dwarfs, rogue planets wandering between stars, or black holes formed from collapsed stars. While these objects certainly exist, exhaustive surveys have scoured the galaxy for their subtle gravitational lensing effects. The result is clear. There are not nearly enough of them to account for the immense gravitational signature of dark matter. They are a drop in the ocean, not the ocean itself. The sole exception here is the theoretical idea of primordial black holes, which are not born from dead stars but from the dense early universe, and they remain a fascinating, though constrained, candidate. Third, a crucial distinction must be made about dark energy. It is not the force of the universe's expansion itself. That expansion began with the Big Bang and has continued ever since, driven by that initial momentum. Dark energy is the name we give for whatever is causing the acceleration of that expansion. Think of it like a car rolling down a gentle hill. The initial push gets it moving, but if you suddenly press the accelerator, the car speeds up. The expansion is the car's motion. Dark energy is the mysterious foot on the accelerator pedal, making that motion faster and faster over time. Finally, and perhaps most importantly, our lack of a final answer is not a sign of ignorance or scientific failure. On the contrary, we have constructed one of the most successful models in the history of science, the Lambda-CDM model. This framework, which incorporates both a cosmological constant and cold dark matter, describes the evolution of our universe from its first microseconds to the present cosmic web with breathtaking precision. It predicts the patterns in the ancient light, the distribution of galaxies, and the accelerating expansion. We are not fumbling in the dark. We have a detailed, mathematically precise map of the hidden architecture's effects. What we lack is the identity of the architect. Knowing how something behaves with perfect clarity, while not yet knowing what it fundamentally is, represents a thrilling and specific frontier, not a gaping void in understanding. Clearing away these misconceptions sharpens the true nature of the mystery, allowing us to fully appreciate the monumental progress that has brought us to the edge of discovery. This journey through the invisible framework does more than fill textbooks. It reshapes our perception of reality itself. Behind every data point on the cosmic map is a person. The search for the hidden architecture is not a cold, mechanical process. It is a profoundly human story, written in long nights and shared frustrations. Imagine a researcher at a remote mountaintop observatory in Chile, the dry air bitingly cold, their only companion the hum of the telescope as it tracks a distant galaxy cluster. Or picture a graduate student in a windowless room, staring at a screen filled with the jagged lines of data from a deep underground detector, hoping to see a single, anomalous blip that no one has ever seen before. For these individuals, the work is a marathon of meticulous care, punctuated by moments of intense camaraderie and the rare, electric thrill of a possible signal. That thrill is always tempered by discipline, for the most likely outcome is that the signal will fade with more data, revealing itself to be just another trick of the background noise. This cycle of hope and rigorous skepticism is the heartbeat of the scientific process. It is a global endeavor, connecting teams from Tokyo to Toulouse, from California to Cape Town, all speaking the universal language of curiosity. They are united not by a quest for personal glory, but by a shared, humble desire to read the blueprints of reality. For you, the viewer, engaging with this story is an invitation to join that quiet, persistent wonder. When you next look up at the night sky, you are no longer looking at a static postcard. You are witnessing a dynamic, ongoing construction project of unimaginable scale. Those pinpricks of light are temporary decorations on a framework that is mostly invisible, a scaffold built from a substance we cannot touch, expanding under the influence of an energy we do not understand. This knowledge does not diminish the beauty, it deepens it with meaning. It expands your personal sense of scale, connecting the everyday world to the grand narrative of cosmic evolution. It stretches your sense of time, linking you to a story that began nearly 14 billion years ago, and whose final chapters are still being written by forces we have only just named. This personal connection, this feeling of being a conscious part of an unfolding cosmic mystery, is perhaps the most profound gift of this entire scientific journey. It transforms us from passive observers into active participants in the greatest detective story ever told. So let us now gather all these threads, from the spin of galaxies to the stretching of space, and weave them into a final, unified vision of the cosmos we call home. Our exploration of the hidden architecture of the cosmos reveals a universe far stranger and more magnificent than we ever imagined. We began with a beautiful lie, the night sky we can see, and discovered it represents less than 5% of what truly exists. The rest is a grand, invisible framework, a silent dialogue between dark matter's relentless pull and dark energy's accelerating push. This dialogue wrote the entire cosmic story, from the first gathering of gas in primordial halos to the majestic spiral of our own Milky Way. It dictated a timeline where galaxies could form and life could arise in a narrow, precious window of cosmic history. We are living in that window, during the tail end of the age of structure, at a time when we can still see the grand design and ask questions about its origins. This understanding transforms a simple glance upward into a profound recognition. Every star is a temporary beacon on a scaffold we cannot see, every galaxy a node in a web woven by gravity we cannot feel directly. The universe is not a collection of isolated objects, but a single, dynamic entity, its evolution choreographed by these dominant, unseen partners. Our journey has taken us from the stubborn orbits of stars at the edges of galaxies, a clue first grasped by, to the ancient light of the cosmic microwave background, a fossilized map of the infant cosmos. We have used gravitational lensing to chart the geography of invisible mass and built synthetic universes inside supercomputers to test our theories. We have confronted staggering mysteries, like the cosmological constant problem, where our best calculations are off by a number with 120 zeros, and the haunting fine-tuning that allowed our universe to be habitable at all. These are not dead ends, but signposts, pointing toward a deeper layer of physics we have yet to uncover. The fundamental nature of dark matter and dark energy remains the greatest open question in science. Are they new particles, like Axions or WIMPs? Are they manifestations of modified gravity or properties of quantum vacuum? Or does their explanation lie in a multiverse of unimaginable variety? We do not yet know, but to say we are ignorant would be a profound mistake. We have constructed the Lambda-CDM model, a framework of stunning predictive power that describes the universe's evolution with breathtaking precision. We know how the hidden architecture behaves. We have mapped its shadow across the cosmos. We are now in the golden age of cosmic cartography, with tools like the Observatory, the Roman and Euclid telescopes, and future missions like LISA and CMBS-4 poised to transform our blurry map into a sharp, three-dimensional blueprint. They will measure the equation of state of dark energy, decide between a slow freeze and a sudden rip for our cosmic future, and perhaps hear the gravitational waves from the universe's first second. This quest is more than a technical endeavor. It is a fundamental part of our cultural and philosophical landscape. It reminds us that curiosity is our greatest instrument. It drives technological innovation, from ultra-pure materials to revolutionary data science that flows back into our daily lives. It fosters a cosmic perspective, a humbling and inspiring view of our place in a reality mostly made of something other than us. You are part of this story. The next time you look up at the night sky, see it not as a static ceiling, but as a living, evolving construct. You are witnessing the visible signature of an invisible dance, a dance that began nearly 14 billion years ago and whose final movements are still being composed. Wonder about the dark matter halo that cradles our galaxy and the dark energy that stretches the space between the stars. That sense of wonder is the first step in a journey that connects us all to the grandest mystery there is. We would love to hear your thoughts and questions in the comments below. What part of this hidden architecture intrigues you the most? If you found this journey through the cosmos's secret blueprint fascinating, please subscribe for more deep dives into the universe's greatest mysteries. Thank you for watching.